Yesterday, we started looking at first partial derivatives. And we discussed that there are going to be a function of two variables will have two first partial derivatives. There were three aspects of things we need to look at. Yesterday, I pointed out two, but then I remembered at the last minute there's a third, and that's notation. First, we need to deal with the notation, because math is all about the notation. Second, there's the thinking about partial derivatives and what they tell us. And third, there's the mechanics of finding partial derivatives. Clearly, that's going to be the most important one because that's the one that like shows up on tests and stuff. So that tells you right away that in your future job as an engineer working on the mission to Mars, you're going to have to find by hand first partial derivatives. I don't think that's actually true. I wouldn't know because, I mean, what job have I ever had besides this one? I mean, okay, I've delivered pizzas before, so there's that. And I've also loaded trucks before. I was very bad at that one. That was a lot of work. I'm not into jobs that are like a lot of work. That's why I like this one. Oh, wait, that's not what we're supposed to say. Oh, this is so hard. Oh my gosh. Let me put my hand against my forehead and lean back slightly to indicate how hard and stressed this is. So we've got the notation, we've got the thinking, and we've got the finding of partial derivatives. We do have to do the finding of the partial derivatives, not because we're going to be doing that in the future, but because we can't have conversations if all we can do is like planes. If all we get to deal with is linear functions, then we can't have really conversations about what's going on. So the good news is that once we get used to the notation, that's the newest part of this whole thing. The notation is the newest part, and it's still just modifying the old notation. Once we get used to the notation, the thinking is still the same. Derivative tells us the direction at a point, but now that we have a surface and not a curve, we have two different directions. We've got an x direction and a y direction. And then eventually combinations of those. So we got 360 degrees of direction we could think about. But right now we've got an x direction and a y direction. The other good news is that in terms of the mechanics, you already have the mechanics. You already know how to do this. Yesterday, when we find the partial with respect to x, we're going to treat y as constant, either a term or a factor. When we have a partial with respect to y, we're going to treat x as constant, either term or a factor. So when we take the derivative with respect to x, y is constant. Term or factor. We treat constant terms and constant factors differently. Constant terms, the derivative is 0. Constant factors, they just get carried along. When we take the first partial with respect to y, then x is constant. Term or factor. Two different ways that we can include a constant. The derivative of a constant factor just gets carried along because the derivative is still a linear transformation. So the derivative respects scalar multiplication and vector addition. So the derivative of a constant times a function is that constant times the derivative of the function. All the other rules that we had before are still in play. So there's still a chain rule, product rule, quotient rule. So yesterday, if you recall, if our function of two variables had an x to the third, y to the fifth, I think this is probably the one that we did because it's the one that I always do because I don't have like a lot of creativity. We had two derivatives, partial with respect to x and partial with respect to y. When we take the partial with respect to x, we're going to treat y as a constant. In this case, y is a constant factor because it's being multiplied by the x cubed. So fx, using our modified prime notation, will be 3x squared times y to the fifth. We just carry the y to the fifth along. It's a constant factor. So in this one, we're looking at this as y to the fifth is a constant factor. We want the partial with respect to y. X to the third is the constant factor. So the derivative of y to the fifth is 5y to the fourth. And x to the third is a constant factor. Then the other thing we do is rearrange this so it looks like a proper monomial, and we don't put the 5 in the middle of as the middle factor. We like our constant factors to be out in front. So in this one, x cubed is a constant factor. Then we have one where we separated things out into terms. Now we're going to treat whatever variable we're taking the derivative with respect to. The other one is constant, but in this case, it's going to be a constant term. So your partial with respect to x is 3x squared. But now y to the fifth has no x in it. That term has no x in it. So the derivative is equal to 0. Then the similar thing happens to x cubed plus y to the fifth. We take the derivative with respect to y. The derivative of x cubed is 0 because x cubed is a constant term. We wouldn't write this. And we just take the derivative with respect to y, which is 5y to the fourth. And x cubed is a constant term. Derivative of a constant term is 0. All we have to do now is combine this with all the other things that we know. One of the things that we know is the chain rule. If we have a composition of functions, when we have a composition of functions, we need to use the chain rule. In fact, we're always using the chain rule. It's just that sometimes the derivative of the inside is 1, so we don't worry about it. Sometimes that du dx is just 1, so we're not worried about it. It's more of a dx dx, which is going to be 1. But here we got the chain rule. The derivative of sine of something. If I want the derivative of sine of something, the derivative of sine of something is cosine of that thing. Times the derivative of that thing. And in this case, the derivative of x cubed y to the fifth with respect to x is 3x squared y to the fifth. If we want to find the derivative with respect to y, we still got to use the chain rule because we always got to use the chain rule. The derivative of sine of a thing is cosine of that thing times the derivative of that thing. We would probably want to clean these up because our monomial, we should probably write as the coefficient of the cosine, but those are just a matter of style. Chain rule is always in effect. Derivative of sine of something is cosine of that thing times the derivative of that thing. Similarly, if we had some function, say g of xy, that was the sine of x cubed plus y to the fifth. We do the same thing. The derivatives of the inside will be, instead of be 3x squared y to the fifth, it'll just be 3x squared. And the second will just be a 5y to the fourth. If you're starting to feel that today might be kind of death by examples, that is correct. Today is about death by examples. Once again, we get this 3x squared, just the 3x squared, because y to the fifth is a constant term. We're not doing anything new so far as the chain rule goes. That'll show up when we get to like second derivatives and higher end derivatives. But for right now, questions? Nothing new here. It's just about how we see what's going on. When you're finding the derivative with respect to x, you look at y as just a constant, as any other constant. You're concerned with how things are changing in the x direction, and that's unaffected about what's going on, how things are changing in the y direction. That's the important interpretation of what's going on. When you're finding the partial derivative with respect to x, you're thinking about what's happening if I just change the x value. As in these x directions, I'm pointing along the outside wall for those of you at home. That's the x direction that I've decided on. We only care about how the surface is changing in the x direction along this line for a fixed value of y. Then we just turn 90 degrees and say what's going on as we change in the y direction. We're not worried about how things are changing in the x direction. We're just worried about one line. Change one thing. Then after this, for those of you who are worried about it, we will figure out how to take those two directions and combine them and figure out how things are changing in any direction. Yes, the chain rule, we use the chain rule on these two examples. How's everybody okay? Easy, right? I told you Calc 3 was the easy one. When you're working on mechanics, the examples are just so out of left field. You just want them to do a certain thing, and then you're like never going to see these functions again. very strange. You're just designing, these are bespoke functions just to make you do the thing. Do you know what I mean? It's like, think back to your algebra class. Do you remember learning how to factor, how to unfoil something, find factors of C whose sum is B and all that? Factor x squared plus 7x plus 12, right? The problem is we want you to know that this is something that we can do, right? So I give you a bunch of factorable polynomials, and maybe like 1 in 10 are not factorable, because I want you to know that we can't always do the process, right? So in your algebra training, you get like tons and tons of factorable polynomials so you can practice the skill and develop the skill. The problem is it completely skews your perception about factorable things. Because if we start picking polynomials at random, the probability that they're factorable over integers like we did is 0. You can't just like come up with a random polynomial and have it be like actual random, not like a human coming up with a polynomial. Because humans are biased towards factorable polynomials because that's what you see most of the time. Most of the polynomials that you run into, at least when you first step into a calculus class, are factorable polynomials. And it's given you this skewed view of the world of polynomials. You know what I mean? It's implicit bias that we programmed into you because we wanted you to practice doing the thing. I don't know what point this function has other than we're going to use the product rule on one of the derivatives, but not the product rule on the other one. That was all just a lead-in to make you think about what's going on. Let's suppose we want to find the partial of p with respect to x. What rule do we have to use? Especially since I just said it. Product rule. Why do we have to use the product rule? Because this x to the fourth, and it's being multiplied by sine of x to the third. I got a function of x and another function of x. So we're going to use the product rule. So for px of xy, we're going to use the product rule. The derivative of the first, why do they have to be completely red? They don't. Stop using the red. No, keep using the red. It's like the fight going on. The derivative of the first times the second plus the first times the derivative of the second. What do we have to do on the derivative of the second? What do we need? Chain rule, because we always got to use the chain rule. Did we have to use the chain rule on this first term? We did. We always use the chain rule. It's just that the derivative of the inside was 1, so we didn't write it. That was a trick question. That's a dirty trick on my part. When your teachers give you trick questions, they're just being dicks. If they do it on a test, they're being assholes. Don't put trick questions on your tests. It's just stupid. Here's what it sounds like when a teacher gives you a trick question on a test. I'm smarter than you. I know more than you. That's what you sound like when you put a trick question on a test. When you do it in class, you're just being silly because you're going to point out, and I'm going to point at myself. It's like, I'm being a dick when I say, aha, it was a trick question. But there's no stakes. And I am casting myself as the villain. But when there are stakes, when there are points at stake, and you put a trick question, fuck you. I mean, we all know that the teacher is supposed to know more than the student. That's why the student hired the teacher. You hired me because I know Calc 3, and y'all are trying to learn Calc 3, right? It's like, can we just stipulate that I know more calculus than you? Not a brag, it's just a fact. I will also stipulate that because of our ages, y'all are smarter than me. You have way more potential than me. My brain just does not work as well. It's like old, and it's like calcified, and there's all kinds of stupid ideas that I've been programmed with. Later on, you're going to have to deal with the stupid ideas that you've been programmed with, but that's your problem. Right now, your brain works better than mine does. You know what I mean? This is just facts. But I'm the one that knows calculus, so that's why I'm here. So we would want to clean this up. I mean, because look at this. This is a horrible mess. This is a terrible mess. And I also wrote sine instead of cosine, and no one caught it. So minus 1,000 points for everybody. It's going to be hard to dig out of that hole. I know. There are only 1,000 points on the whole semester, so. Whew. Maximum points, 0. Yeah. It is. It's power play. It's just like, aha, I know something that you don't know. It's just a dick move. If you're doing it for fun, if it's like a bonus question, it's like, oh, here's an extra point, then it doesn't matter, right? Then who cares? It's like, but trick questions are like, oh, hey, have you heard this one before? And when you get it right, you're like, oh, yes, I have. And when you get it wrong, you're like, oh no, I hadn't heard that one before. But now it won't work on me again. See, simple. If you're doing it for fun, then it's fun. If you're doing it for stakes, then you're being a dick. So we use the product rule for Px. We needed the product rule for Px because I have two functions of x. I have a product of do we need the product rule for the partial with respect to y? Not a trick question. I'm not being a dick about that. We can avoid the product rule for the partial with respect to y. And why is that? No, it's correct. Because this x to the fourth, it's not a function of y, or it's a constant function of y. I guess once I do one trick question, I have to be super careful with my language the rest of the fucking day. It's really annoying. That's the other reason I don't like them. For the partial with respect to y, we can interpret x to the fourth as a constant factor. It's a variable factor for px. So since it's a variable factor, we got two variable factors. Product rule. Product rule is for two variable factors. But for the partial with respect to y, x to the fourth is a constant factor. So for py of xy, x to the fourth is just a constant factor. The derivative of sine of a thing is cosine of that thing times the derivative of that thing with respect to y. And I wrote it in some funky order. With respect to y, x to the fourth is a constant factor. We can use the product rule, but in this case, if we use the product rule with the first factor as x to the fourth, the derivative of x to the fourth with respect to y is 0. So if we did use the product rule, we would be fine as long as we recognize that x to the fourth is constant with respect to y. If we use the product rule, we would be fine, but we would have to recognize that the derivative with respect to y of x to the fourth is 0. That makes sense? And the reason I don't want to point that out too much is that if you start thinking of the product rule, you're not going to do that. That's kind of like the little catch-22 there. But technically, we did use the product rule. It's just that the derivative of one of our factors was equal to 0, so we didn't worry about it. All the rules are always in play all the time. Any questions? These could also stand to be cleaned up. Yeah, they look terrible. Our two first partials could also use an algebraic cleanup, but I didn't. Like I've got factors of x over here and factors of x way over here. I've got my coefficient monomial sitting over here at the end. If we start getting sloppy with our parentheses, and all this shit goes into the parentheses, and it's just. Whoa. So I wouldn't, the question was, do we always find x and y? We are, because that's what we're practicing, but I wouldn't say something like find the derivative of p if it's a function of two variables. I would have to say find both first partial derivatives, or find all first partial derivatives if I happen to sneak in a function of three variables. But I would say find all first partial derivatives. I wouldn't be able to just say find the derivative. That's not a well-defined statement. Any question? How's everybody okay? Once you remember your basic rules, product rule, quotient rule, chain rule, and your power rule, the only skill you need to add to that is reading which variable is constant factor or constant term, and whether it's a constant factor or constant term. The only way to make this more complicated now is just make the functions more complicated. And now we're just being silly. Constant factor, the difference between constant factor and constant term. That's a great question. So a constant factor, so this one, this is me being silly. If you're like, oh, dude, that's not very silly at all. I'm like, oh, okay, fine. If you don't like that as being not silly enough, then here. Now it's extra silly. If that's still not enough, I can keep going. My point is that you have all the derivative rules. You've got product rule, quotient rule, chain rule, and all of your base model derivatives. There is not a function that I can put together that without sufficient motivation and time, you can't find both first partial derivatives. You can do it. You have every tool that you need. Like if I start putting functions together and ask you to integrate them, I might just write one down that does not have an integral. There are some functions like, oh, nope, this is not the derivative of anything. But if you want to find the derivative, you can do that for any function. Because you've got product rule, quotient rule, chain rule, and differentiation is the easier direction. Going backwards, blah. Yeah. Yeah. So, of course, the most important thing to do is if the question just says find an antiderivative of the function. No. Just remember your fundamental theorem of calculus. Construct one with the definite integral. So capital F of x is the integral from 0 to x of whatever the funky function is, dx. And be like, all done. I had a student do that to me. I had a quiz where it was like, I'll find the antiderivative, find an antiderivative, because I didn't care about the plus c. I thought, I'm just going to say and to remind you that there's the plus c, but see if anybody notices. But I just said find an antiderivative. The problem was the day before I had just talked about the fundamental theorem of calculus and showed people how to construct an antiderivative using the definite integral. One student just did that. They wrote exactly what I wrote, but they integrated from 0 to x dx. I'm like, oh, holy shit. Full credit, full marks, because that's what I said. And that's what the second part of the fundamental theorem of calculus is for. So anyway, See, that's the good thing. Trick questions from me, bad. Trick answers from students, good. Unless you're deliberately knowing something that we know we're talking about, right? Anyway, so the difference between constant term versus a constant factor. So x squared plus c. So that plus c is separated by, is its own term. It's not being multiplied by the x squared. It's included by addition. A term will be included with addition. And so when we take the derivative of the term, a constant term, we get 0. But in a constant factor, a constant factor is included by multiplication. So the derivative just carries along. This is relevant because terms and factors are treated differently with the derivative. So the derivative of x squared plus c is just 2x, but the derivative of kx squared is 2kx. Derivative of a constant term is 0. We don't normally write plus 0, but I want to emphasize that's the difference here. But differentiation, the derivative, is a linear operator and so respects scalar addition. Scalar multiplication. As a linear transformation, the derivative respects scalar multiplication. The derivative of a constant times a function is that constant times the derivative of the function. A lot of times we do things, it's good to say these things, point these things out, because a lot of times we're doing things in math that we just kind of internalize and kind of automatically do. But we do need to think about them once in a while to make sure that we're thinking about things correctly. That's the part that's hard to see, like how you are thinking about derivatives and things like that, how you are reading functions. It's hard to see sometimes. And a lot of times the way we find out, we test on your mechanics, but it's much harder to find out what you're thinking because I'm not allowed to read your minds. I go, Leach, you can't use your telepathic powers and read students' minds. I go, come on, how am I supposed to tell if they're thinking right? I go, you don't get to know. And that's like one of the struggles as a math teacher. You don't get to know. I can test your mechanics by like giving you this, but at a certain point, I'm not testing your mechanics anymore. If I say find the first partial derivatives of this stupid function, what am I really testing? Not really the same thing over and over because it's only 2, right? How much can you keep track of? how long is your attention span? That's really what this goes after. How long is your attention span and focus for one problem? How long can you keep how long can you keep track of all the dumb shit going on in this function? That's really it. And if you lose track in the middle, do you understand the process well enough that you can go back and see what you've done? Is your notation clean enough? Is your writing clean enough that it represents your thinking? That's kind of what's going on if I ask for those first partials. I promise not to ask for the first partials. He said, lying to his students. Wait, I'm not supposed to read that part. And the reason that I can't just ask what you're thinking is that a lot of times you'll just find like the clip of the clip from the video and just type what I said. And it's like, oh, yeah, but did you write that or did you just transcribe that? Or if it's like a whole paragraph long and I expected one sentence, I might go, dude, you got to edit your ChatGPT responses. It's like, come on, man. Don't just copy and paste from ChatGPT. I like the dude that copy and paste from ChatGPT and the ChatGPT response opened up with like, oh, I'm just a chatbot, but, and you just copy and paste, right? So anyway, it becomes like super obvious because I don't have extensive conversations with you, but no one talks like that. It's the same thing with Wolfram Alpha. Like when you were using Wolfram Alpha just to find antiderivatives, it's like, I don't want to do trigonometric substitution. Hey, Wolfram Alpha, what is this antiderivative? And it's like, oh, you'd have to use trig substitution. I'm like, well, I don't care about that part. I'm not paying for Wolfram Alpha. I just want the free version that will tell me what the antiderivative is. And then you just copy it exactly. And it's hilarious because Wolfram Alpha does some weird shit in its responses. Not incorrect stuff. When you do that, your answers are correct, but they're not human. Like if there's a factor of a 1/9, you factor that out, but there's also a factor of e to the 3x where that 9 came from, and you don't factor that out. I'm like, oh, obviously, you got this from Wolfram Alpha. It is so obvious because no human would write some things like Wolfram Alpha does. You know what I mean? It's super obvious. I just want you to know that. Sometimes it's fine. Like if you ask that Wolfram Alpha what the derivative of x cubed is, it'll tell you 3x squared, nothing funky going on. But if you start getting into the rules, because it's working with a computer brain and not a human brain, it writes things really weird sometimes. And it's just super obvious. You know what I mean? And the other teachers would be like, oh, how do you know that this, if you have them do the homework at home, how do you know that they're just not getting their answers off of Wolfram Alpha? And I'm like, well, I don't. I literally don't. And I can't police that. It's just like, that's just like something that is going to be, I've accepted that that's out of my control. If you just want to get your answers off of Wolfram Alpha and type them in, that's on you. I can't police that. Because it's a different thing if I ask you to come in here and do the problems in front of me with me watching you and the time's going on and the only sound is the humming of the fluorescent lights. And the only light is this, right? And we're all doing this problem silently and everybody's doing the same problems and we're writing it down on paper. That's a lot. That's at, once again, now I'm not testing what I want to test. I'm testing how good you are at taking tests. Sometimes we want to know that. How good are you at taking tests? But that's what I'm testing in that moment. It's less about what you know on that day and more about how well you deal with that, because some people do not deal with that very well. Like if it's perfectly quiet, we're all sitting here doing problems and I do this, I just ruined your concentration. For some people, that would just be enough to ruin your concentration. You know what I mean? If we're like doing some problems and it's all quiet and someone finishes their test, they turn it in and walk out. Some people just like keep going. It's like, oh, I guess that guy's done. And for some people, they start thinking, oh my God, I'm the only one taking so long. Meanwhile, there's like 30 other people in the room still working on the problem. But you think in your mind, you're like, oh, I'm the only one that's taking so long. I'm so slow. But one person got up and walked out. And now that's what you're thinking about. Do you know what I mean? So when a question comes up, how do you know the students are just using Wolfram Alpha to do their homework? I don't know if that's the case. All I can do is ask them not to. Have some respect for yourself. I don't care about me. You don't have to have respect for me. Have some respect for yourself. You're trying to learn stuff. So try it. And then my responsibility is to make an environment where when you get things wrong, you get to try again. Because that encourages you to do it again. You know what I mean? You get the behavior that you reinforce. And if you start making penalties, if you start applying punishments for students getting things wrong, they're just going to be afraid to get things wrong. That's it. And I don't want a room full of people that are supposedly studying science of all things, to be afraid to be wrong. You cannot be afraid to be wrong. Not if you're going to play the science game. The science game is all about being wrong. You're going to think about something. It's like, oh, how do I prove myself right? Nope. How do I prove myself wrong? How do I prove that I am wrong? So don't be afraid. You can't be afraid to be wrong. We have to set up some kind of system where you're not afraid to be wrong. It has to be not devastating when I'm like, oh, that is incorrect. Do that again. You're like, all right. I get to fucking do this again. Yeah. I mean, that's maybe a little too far. But, you know what I mean? What if I did it differently this time? I know that I just dinged level 50 on my rogue, but what if I went back and tried it this way and did it this pattern? New level 1 character appears. I may have a problem. Any questions? Comment? Deep thought. I love Wolfram Alpha. It does write things weird. So if you're just copying, that's bad. But if you're like, oh, did I do this right? It's a great way to check. And it's also really good because you'll learn what messed up things Wolfram Alpha does when it writes its weird ass answers. It's like, oh, that's Wolfram Alpha doing some Wolfram Alpha shit and writing it real weird. And you start recognizing it. And then doing that, it makes you better at algebra. I know you think you're good at algebra, but I assure you, most of you are terrible at algebra. You know enough algebra to get by, but I trust your algebra skills at this point about as much as I trust your driving skills. Yeah, I'll get on the road with you, but I'm going to watch out. I'm going to be watching out. You know what I mean? Oh, look. There's a young man in his early 20s driving a Honda Civic. Yeah, I'll just stay away from that guy. Just going to avoid that one. Oh, no, he's pulled up next to me at a stoplight. I'm not even going to look over. Because that's just going to encourage them to like take off like a bat out of hell from the stoplight. You know what I mean? This is what happens if you drive like a Subaru or some shit. Not like a Crosstrek, but I drove a Subaru BRZ and I just couldn't look to the side. Especially like when some dude in a Corvette pulls up. I'm like, oh, I fucking know, dude. You have twice as many cylinders, 3 times the displacement, and you paid twice as much for your car. So I revved my engine to try to get him a ticket. Actually, it was a Subaru. And I go, blah, 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 Corvette, blah, 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 blah. And I go, don't do that with Mustangs if there are people standing around. Because the Mustang will just crash into the people. I'm not making fun of Mustang owners, if there are any Mustang owners here. I'm making fun of the other Mustang owners. All right, that's it for today. Remember, when you're doing Calc 3, You know how to do the things. We're just modifying it a little bit. That's it for today. I'll see you all on tomorrow. Everybody have a good day. And thanks for playing. Drive carefully, please.